Hello everyone, welcome to my channel Physics with Bhatt. To learn concepts of physics, subscribe this channel and press the bell icon button to notified of every new video. In the last video lecture, we discussed about the conditions for constructive and destructive interference. We have analyzed with the help of the detailed analysis mathematically as well as conceptually. Try to understand that in what condition the constructive interference occurs and under what condition destructive interference occurs. Today in this video lecture we will go through one experiment that was done by Young. In this experiment he tried to explain all the things related to the interference, constructive, destructive, with the help of an experimental arrangement. For the purpose, you can see here in the diagram, he had taken one monochromatic source which is denoted by S here. This is monochromatic source of light. This monochromatic source is used to illuminate two slits S1 and S2. These are two fine holes made in a sheet, and then a screen is placed at little distance capital D away from the plane of the slits. So monochromatic source means the source which is providing the light of single wavelength, that is called monochromatic source. When this light is illuminating these two slits, passing through them, they superpose each other, we get two waves originating from S1 and S2. You can see in this schematic diagram as well. Here we have the source S. These are two slits S1 and S2. The separation between these two slits S1 and S2 is small d, and the screen is at capital D distance from the plane of the two slits. So when these waves originate from the S1 and S2, these are two coherent sources because the distance between screen and plane of slit is not changing. Moreover, the distance between two slits is also not changing, as well as the source is also at fixed distance. So in that way, these two sources will act as two coherent sources. The waves originated from S1 and S2 superpose each other. For the instant, we take point P where they are getting superposed, and so this point P will be bright or dark, that we will try to understand here, and we will use the conditions obtained in the last video lecture for the constructive and destructive interference to take place. So the arrangement is very simple. There is no specific, you can say, arrangement or a very complicated arrangement here. We just have only two slits, and these two slits are illuminated by the monochromatic source. Now we will deal the diagram mathematically. As we know that for the constructive or destructive interference to occur, path difference and phase difference are very important. So here we can find path difference between the two waves originated from S1 and S2. For the purpose, we will use a right angle triangle. You can see here the distance of a screen, this GG dash is screen, S1 and S2 are two coherent sources. Path difference between the two waves is S2P minus S1P. If you just see, if you join this point is Q and this point is R. If we consider the triangles S1PQ and S2PR, then we can use Pythagoras theorem to find the path difference S2P minus S1P. This is the path difference between two waves originated from the sources S1, S2 and superposing at point P. So our point of interest P is here, and we will just find out that for what value of position X we will have constructive interference positions, and for what expressions or values of X we have point P is the position of destructive interference. So let us use Pythagoras theorem for these two triangles. So first I will consider the triangle S1PQ. In triangle S1PQ, S1P square, it is hypotenuse square, is equal to S1Q square plus QP square. S1Q is D and QP is equal to X minus D by 2. This point is symmetrical. The distance between S1 S2 is a small d, so the distance OQ would be D by 2. So QP is equal to OP minus OQ. OP is X and this is minus D by 2. So we would have S1P square is equal to D square plus X minus D by 2 whole square. Similarly, in triangle S2PR, the triangle S2PR here is, and we are using the same Pythagoras theorem, so we will have S2P square is equal to S2R square plus PR square or RP square. S2R is equal to capital D and RP is equal to OP plus OR. So RP is equal to OP is X and OR is again D by 2. Then S2P square is equal to D square plus X plus D by 2 the whole square. Now S2P square minus S1P square, this would be D square plus X plus D by 2 square minus D square minus X minus D by 2 square. What we have done? We have replaced for S2P square and S1P square. So this D square is cancelled. So D square is cancelled. Then what will left here? S2P square minus S1P square is equal to X plus d by 2 square minus x minus d by 2 square. If you deal right hand side by using identity a square minus b square, you would get x plus d by 2 plus x minus d by 2 and x plus d by 2 minus x plus d by 2. So in first bracket d by 2 is cancelled, you will get 2x, and in second bracket x is cancelled and d by 2 plus d by 2 is d. That gives us s2p square minus s1p square is equal to 2xt. If we deal with this left hand side also, so we'll have s2p plus s1p into s2p minus s1p is equal to 2xt. So s2p minus s1p is equal to 2xd upon s2p plus s1p. For point P close to the center of the screen, S2P is nearly equal to S1P is nearly equal to capital D. It is an approximation that we are following here. So whatever result we will get at the end, those are the approximate positions. Then S2P minus S1P is equal to 2xd upon d plus d. So you would have S2P minus S1P is equal to 2xd upon 2d. 2 would be cancelled here. So S2P minus S1P is equal to xd upon capital D. We can replace for this path difference. Path difference here is S2P minus S1P, and for this we can take the symbol y. Therefore, path difference y is equal to xd upon capital D. Now we will use one more important result that will connect this path difference to the phase difference. And then phase difference phi is equal to 2 pi by lambda into y, and y is xd upon capital D. Now we will use the condition of constructive interference for the constructive interference phi is equal to 2n pi. then point P will be the position of maximum due to constructive interference. Then 2n pi is equal to 2 pi by lambda into x d upon d. Pi will be cancelled, 2 pi will be cancelled, so n is equal to x d upon lambda d. If you cross multiply, x d is equal to n lambda d, which implies x is equal to n lambda d upon d. So this is the position of maximum, that is constructive interference. So here you can put n is equal to 1, 2, 3 and so on. If you put n is equal to 1, you will get the position of first maximum. If you put n is equal to 2, you will get position of second maximum. If you put n is equal to 3, you will get position of third maximum. On the other hand, if phi is equal to 2n plus 1 into pi, then destructive interference occurs and point P will be position of minimum. In that case, we will have 2n plus 1 into pi is equal to 2 pi by lambda into x d upon capital D. This time pi would be cancelled, so you will have 2n plus 1 lambda d is equal to 2xt, which implies x is equal to 2n plus 1 lambda d upon 2d. So this is the position of here n is equal to 0, 1, 2, 3 and so on. It is the position of minimum due to destructive interference. So in this video lecture, we discussed a very easy concept of using the diagram, and the diagram is related to Young's double-slit experiment. Here we have established the expression for the positions of constructive and destructive interferences. In the next video lecture, we will discuss about in detail that what is the fringe pattern or the pattern on the screen we are getting due to the constructive and destructive interferences, and we will describe the whole pattern here. Thanks for watching this video. Keep watching, keep learning.